Welcome back to CS520. In this session, I'm going to talk about reading maTe class files. So this builds upon the last video lecture, which was about the representation of maTe programs. And we're starting to talk now about implementing the maTe virtual machine. Of course, this lecture will also be useful if you are trying to write a disassembler, perhaps, for the maTe class files. But in the context of implementing the maTe virtual machine, reading the class file is really step number one. As you initialize the VM, you're going to suck in the class file into memory and also do some processing of it to make the pieces of the class file accessible to the rest of the program. And what is the rest of the program? There'll be a follow-up lecture to this one that talks about the rest of the VM implementation. But let me just give you a little overview of what that is all about. So the initialization phase that I just mentioned will be focused on today. And then there's obviously an execute phase, right? We actually have to execute the program that's inside the class file. And to do that, we really need support from three major modules. One of them is functions to provide access to the information in the class file. And this is also going to be discussed in this lecture. So as well as reading the class file, we're going to talk about implementing a set of functions to provide access to the information in the class file. Things like the class table, for instance. But there's two other kind of support components that you need to implement in order to implement the VM. And that's some support for the heap. So how do you allocate objects? Again, maTe is a pure object-oriented language, so everything is an object. Everything will be allocated in the heap. So you need support for allocating objects. And the heap would interact with a garbage collector that would be executed when you run out of memory in the heap. Again, we'll talk about garbage collection in later lectures. And finally, the third component that you would build up on is support for frames and a runtime stack of frames and then an operand stack inside each frame. So again, a frame is there's a frame created for each method invocation. And it contains things like the save program counter, local variable slots, and then the operand stack, because maTe, like Java, is a stack-based machine. And finally, on the bottom here is something I mentioned last lecture, which is that there's native code to implement the four native classes or the four built-in classes. And the execute engine will rely on that as well. Okay, but today I'm going to focus on reading the class file and then implementing these functions, these support functions to provide access to the information in the class file. So my recommendation is, you approach this by just read the whole class file into memory. If you remember, the class file itself is a sequence of 32-bit integers, so it makes sense to just read the whole class file in, place it into an array of 32-bit integers, which becomes effectively the virtual machine's memory. So you're implementing this maTe virtual machine, and its memory will consist of this array of 32-bit integers. So inside your virtual machine implementation, you're going to have a data structure that represents the virtual machine's memory. Okay. One advantage for reading the whole class file into memory up front is you can deal with the endianness. Again, the class file is a sequence of 32-bit integers, but those integers are represented in a file, which is, of course, byte-oriented. So the maTe designers decided to make the integers be stored in big endian format. So as you suck the bytes out of the file, you can take care of that endianness, put the bytes together into the 32-bit words, and then just store the words in your data structure, in your array, so that when you're executing, you don't have to worry about the representation, the endianness of those integers. At that point, the bytes are all put together into 32-bit chunks themselves. In fact, you need to probably read the class file twice, because this data structure here, you don't know the length and you don't want to have to set an arbitrary limit for the length. So one simple way to do this is just read the file twice, once to get its length, and then the second time, after allocating the VM memory, you can read the file again and fill in the VM memory. Of course, there's clever ways to do this. You could just access the file length directly, but a simple-minded way would just be to read the file twice. Again, you're trying to figure out how long the file is so you can dynamically allocate this array to the right length, and then read the file a second time and fill it in. Okay, so once you have the class file loaded into memory, then you need to implement these functions, a set of functions that provide access to the information that was in the class file and is now in the memory of your VM implementation. And again, just a high-level view of the class file. Remember, there's three basic sections. There's info about the main block. So there's a descriptor of the main block. And then there's information about all the classes that were defined in the program, including the built-in classes. And then there's the code itself. So the encoded maTe instructions are down in here. These would be instructions for both the main block and for methods for user-defined classes. So there'll be functions to manipulate each one of these sections. We'll take them in turn. And the VM implementation design that we're using has two functions to access the two pieces of information that are in the main block descriptor. There's just the main block address, so where is the code for the main block, and then how many local variables does that main block require. And again, thinking back to last lecture and remembering the details of how the class file is organized, those are just the first two words in the class file, so they'll be the first two words in your VM memory. So those functions are easy to implement because those items are at a fixed location that never changes. All programs that you'll be reading in, all class files you'll be reading in, the main block is in the same location. So that's easy. Those functions are easy. Class table is a little more complicated. All right, what was the structure of the class table? Well, it began with the number of classes, and then there was a class. There was a set of pairs, one for each class, that contained the class descriptor address and the class name. And these are annoying because they're actually variable length. This class name, if we go down here and read this footnote, the class name is a sequence of 32-bit words. There's one ASCII character per word, and then there's a 0 word on the end to terminate the name. So to skip from pair to pair here in this list of pairs, you have to skip over the name because they're variable length. The class descriptor address itself is just one word, and it points to an address down further in the class file or further in the VM memory now. Again, another important footnote, something that will plague you throughout implementing the VM, is that an address is a byte offset. Again, I talked about this in last lecture, but I'll keep reminding you of this because it's going to be something that you'll probably forget at some point. But the address in these class files are byte offsets into the class file. What I'm recommending you do is you load the class file into an array of words. So you're going to constantly be translating those byte offsets into word offsets. And of course that's simple. You just multiply by 4, but you need to remember to do it. Okay. Again, the class descriptor address tells you where the actual detail information is for this particular class. So it's an address further down into the class table. Sorry, into the class table, but also into the VM memory. So then there's a class descriptor for each one of these classes. Okay. Now, one thing important to remember as you move forward with executing the VM is that this class descriptor address is actually how the program will talk about the class. So when an instruction refers to a class, it refers to the class by the class description address. So it has essentially a pointer to the class descriptor for the class it's talking about. And I'll try to remind you of that too, but that's an important fact to understand. Okay, so there's a set of functions here to implement to access information in the class table. So is it a valid class? So again, you have an input here, you have a parameter here, class. What this is going to be is an address for a class descriptor, and is valid class is just checking to make sure that there actually is a class descriptor at that address. So you would go through this list here. It's not a list, it's an array really, right? You have the number of classes, and you have a sequence of these pairs of descriptor address and class name. So to do is valid class, you'd have to go through here and make sure that this address that's being passed in is one of those class descriptor addresses that are described in the class table. Okay. By the way, the interface apparently does not have a function to access the number of classes, but you know where that is. If you ever need to, you're going to need to get the number of classes in order to implement these functions. Obviously, what word is this? This is VM memory sub 2, right? It's right after. Again, we go back to the last slide for a second. It's right after the first two main block words, right? 0 and 1 are the two main block words. So the next thing in the class file is, in fact, the number of classes. It's interesting that the interface doesn't have that function to access it, I guess. And I guess you don't need it inside the execution engine. You're going to be accessing everything through these functions. So what are the rest of these functions? Well, get object class, get integer class, get string class, get table class. These are all void functions that return a class descriptor address. And the trick is that you are guaranteed that the way the maTe class files will show up as input to you is that the object class will be the first class. So it'll be a class at index 0. This one will be number 1. This one will be number 2, and this one will be in number 3 in this table here. Let me just make sure I've got those right. 1, 2, and 3. That is correct. Okay. Then to get user classes beyond that point, you can use this method. Again, I've got the interface wrong there. Get ith class must take a parameter, right? Let me just double check that. Yes, so again, I screwed this up. This should have been int I. Takes I as a parameter and gets the ith class in these lists of pairs to find the descriptor address. Okay. Then there's 4 more functions to just validate if a class is one of the 4 built-in classes. So you pass a class in and you ask, is it an object class? Is it the integer class? Is it the string class? Or is it the table class? So again, you know where these classes are, where their class descriptor addresses are stored, what index into this table of pairs, so you can just check whether this class descriptor matches the class descriptor that you know for object class, and so on. So again, those are all fairly straightforward, but again, the problem is skipping over those class names. They are variable lengths. So you've got to have code that's going to actually jump from descriptor to descriptor. You can't just index in. You can't calculate the address of the next class descriptor. You've got to actually skip over the class names because they're variable length. Okay. All right, so that's the first part of the class table. Let's look at class descriptors. Okay, a class descriptor. So the information about a particular class, the first thing will be the superclass. This again will be the class descriptor address of the superclass. And there's the number of fields then there's a method table. And again, in our interfaces, there's two functions to access those first two fields. All right, so get superclass. Once you've got the class descriptor address, this is just going to be the first thing in it. So this, again, this will be the class descriptor address. So in effect, it points to the word you want to return. So that's pretty easy. This one, you have a pointer to the first word. You just need to return the second word. So again, that's fairly easy too. So those are pretty straightforward. As we'll see, though, the method table itself is a little more complicated. Let's take a look at that. So what's the method table look like? Well, it starts with the number of methods, and then it has a table of triples now, where you have the code address. Where's the code for this method? How many local variable slots does it require? And what's its name? And again, these names are annoying because they're stored just like class names, so they're variable length. One ASCII character per word with a 0 word on the end to terminate the name string. So again, jumping from method table index, one method table level to another, you're going to have to actually skip over these strings. And again, there's in our interface here to implement the class section. Let me just back up to the big picture here, make sure I haven't confused people. Remember, these functions I'm looking at in red here are all functions that define this interface. Why are we doing this anyways? Well, we're breaking a much bigger task into a set of smaller tasks, and we can then test each one of these components separately, and each one of these components will hide the details of a particular feature of the VM so that we can simplify code in other sections. Right? Everything about where things are in a class file will be located in this component. And once we've implemented that and we can do unit testing of it, then when we're implementing the execute engine, we just use those functions and we don't have to worry about the details of where things are exactly in memory or in the class file. So we've got a nice clean design here that helps us sort of separate concerns and separate out the details. Allows us to do unit testing of components and then put the pieces together to finish the VM implementation. So again, the methods then to access the method table, there's a method to, given the class descriptor address, we can get the number of methods. So that's just a certain number of words from the beginning of the class descriptor. All right. That would be the third word. In fact, the class descriptor starts with a superclass and the number of fields. The third thing is going to be the first component of the method table, which is the number of methods. So that's, once you have the class descriptor address, and the number of methods are easily found. Then we have two functions that take an index of which method we're interested in. So it's an index into this list of triples. And we might want to get the method address, the code address, or we might want to get the middle field, which is the number of locals. So given an index, you go looking for it in here. And again, you can't just compute the address. You have to actually search because you have to skip over these method names, which are variable length. That's the only annoying part here. Okay. All right, well, there's one last function in the interface, and it's just to retrieve a word from the code section of the class file. Okay, so given an address, we can get the word from the code section. So again, this address is a byte offset, so the implementation of this is pretty straightforward, right? We would take this address. Before, what did I say? I said we were going to take a byte address, and I think I misspoke, right? I said we're going to multiply by 4. I think what I meant to say was divide by 4. Let's back up to that slide. Where was I? I think I was back here just talking about the class table and talking about this address and this footnote that you have to translate from a byte offset to a word offset. And I think I said multiply, but what I really meant, right, you're going to actually divide by 4 rather than multiply by 4. Okay, so make sure you understand that. So going back to this slide then, I just need to get a word from the code section at a certain address. Again, this is going to be a byte address. I need to divide that by 4 to get the word address. All right, so it's basically the implementation here is the VM memory of the address divided by 4 is what you're going to want to return from that function. Okay, I'm just trying to think of anything else I should be saying here. I guess not for that. So one last slide here, just some suggestions when you sit down to think about this and do this. Again, you got this problem of translating addresses from byte offsets to word offsets, so make sure you understand that. The annoying thing, I think, is you need code to skip over the name strings at various points in time in the class table itself and in the method table, both. And I strongly recommend that you go ahead and put sanity checks in everywhere in the code, because again, you're going to use these functions to implement the rest of the VM, and it's nice to catch errors as soon as possible. So if somebody passes an invalid class address to one of the functions in the class section of the VM, rather than just doing something, returning some value, we like it just to say, you know what, that's not a valid class, and just quit right there, and then you can track down why is a component of the VM passing me a bad class address. It's probably due to some bug somewhere else. Similarly, if someone calls one of these functions with a bad method index, you'd like to know that right away, rather than indexing in off the end of the method table, grabbing something randomly, which is just garbage, and returning it. And then strange things happen downstream, and eventually you figure out there's a bug. But you'd rather catch the bugs as soon as possible. So putting in lots of extra checks into the code you write for the class section, I think, will pay off when you sit down to do the rest of the VM. Another thing you might do is the code address valid. So that last function we were looking at, this function, is this address actually pointing to the code section? You might delimit that. When you read the class file in, you're grinding through, picking up each piece, and you can actually figure out where the code section begins. Right? It's at the end of the class table. So once you've skipped over everything in the class table, you know where the code section begins. And again, you might put a sanity check in to say that if an address comes in, it actually, rather than pointing to the code, it points to the class table. Rather than picking that up and then trying to interpret it as an instruction or something, we'll just flag it as an error immediately and die, because it's probably a bug somewhere else in the VM that we need to go remove. So I recommend putting in sanity checks everywhere that you can think of, so that you'll quickly catch bugs that crop up as you implement the rest of the VM. All right, I think that's what I want to say about the reading the class file and picking it apart and accessing components of it. So let's stop here.